Okay, we're gonna start. Hello everyone, welcome to SIGPwny's Sunday meeting. I will be going over x86 assembly. Already died on me. Yep. All right. Announcements. Next week we're going to be doing binary exploitation, aka Pwn. It's going to be with Kevin for Thursday and Sunday. Another thing that happened, a alum that we had, Ipe, did a talk about learning about the kernel by debugging. That talk is in the talks channel on SIGPwny. Go watch it. He's a really cool dude, really smart. Also, we're going to have an ACM cleanup party. We don't know when, but when we do it, we have 2 DDR pads, one which is owned by Kevin and one which is owned by us, and we can set up DDR in the ACM backroom. So that is in the future. Okay.
Yeah, what's DDR?
Dance Dance Revolution, rhythm games. We love it. All right. Meeting flag. If you're signed up on ctf.sigpwny.com, you can put in the meeting flag. I also have a XKCD about writing at increasing levels of tedium, because God forbid if ASM is easy to write. So I'll give you a couple minutes to put that in. Slides will be posted later if you want to insert it later as well. Okay, so what is assembly? Assembly is like the human readable, like the first level of human readable abstraction over CPU machine codes. At the end of the day, every CPU can only understand binary. And as much as I would love to be able to rattle off binary to you, this is not readable. And we can usually make it a bit easier by like representing it in hexadecimal format, but unless you were born in the 70s, that still doesn't mean anything to you. So assembly is allowing us to give a mnemonic and then what we're applying that operation to. So that string of binary is what your computer will read to add 2 numbers together. With that in mind, we have another level of abstraction, which is C code, stuff that most of you might have probably written if Python's just like somewhat the same, but like C, C++, Java, all that kind of stuff. Eventually, they're going to have to be converted to assembly. And so this function, as basic as it is, gets converted into this mess of assembly, but this is what your compiler is doing under the hood. So when your computer is running programs, there are 3 major structures you need to be aware of. There is the instruction memory, which is where the code is stored. This is the list of bytes that represent the assembly and where your computer manages running its code. The other structure is registers. These are the 16 on x86 64-bit architecture. These are the 16 variables that your computer can operate on at any given time. And finally, there's the stack. The stack is the list of values that is managed like a stack data structure, so first in, last out, where that's how functions are managing its local variables and call structures and so on. So briefly, instruction memory is just a contiguous memory region of executable data. For safety reasons, this data is labeled as read and execute. We don't want programs modifying themselves to change how they run. That would be dangerous. In terms of where it ends up in like memory space, usually it's at a very low address space, below where your programs are running the stack and the heap. And there's a special purpose register called the instruction pointer labeled with RIP, which always points to the next instruction to be ran. That leads us into registers, which again, the 16 variables that our CPU can use. Each of them are 64 bits or 8 bytes wide. Within a function, 14 of them can be used for pretty much whatever you want. There are 2 that are reserved for managing the stack: the base pointer register, RBP, and stack pointer register, RSP. The other thing that x86 provides, which is mostly for backwards compatibility from 16-bit architecture, is we can access the lower bits of each register. So I have this chart here. It's a lot, but every register can be accessed the top 8 bytes, the top 4 bytes, 2 bytes, or 1 byte. They all point to the same value, but it allows you to work with less bytes at a time. And this is as close as you're going to get to types in assembly. There's no such thing as like types past bytes. Yes. Right. So it just means that on the CPU architecture, every bus that exists to read in data is actually 64 tiny wires. And so it reads all that in as one number. So that gives you what, 2 to the 6? No, wait. 2 to the 64. I'm done. 2 to the 64 like possible values for each number. Like 64-bit architecture is the most recent. We were working with 32-bit in like 2005, 2006 or whatever. And so that's kind of what it means when we talk about 64-bit. Anything that the computer operates over is going to be 64 bits wide. It might use less, but most of the time it's going to be working with the 64-bit numbers in memory and on the CPU. Cool. Okay. So next thing is the stack. The stack exists at the top of memory, like very high address, and grows towards the bottom of memory region. But it can't go all the way. The heap and the rest of the code and globals and strings that are in your program are in the way. The reason this chart looks backwards is because semantics in GDB, when you print out the stack, the most recent value will be at the top and then it goes down. So that's kind of why we've made this image the same way. When you read the stack, it's going to be the most recent to the oldest value added to the stack. So if you want to add values, you push to it. Popping from the stack gives you the newest, removes the newest element that you added. So that's kind of what the stack is meant for. So if you've done some computing class with C++ or Java, everyone will tell you the stack is automatic. The locals get automatically deallocated. Assembly is at the level where that is no longer as automatic. There are 2 registers dedicated to managing it. Again, the stack pointer, which if you want to allocate memory on the stack, you subtract from RSP, and to deallocate, you add to it. And so whenever you want to make more room on the stack, you have to apply that operation on RSP. There's a couple commands that does it for you, but all in all, you are now responsible for managing your own stack. RBP holds the address at the start of the stack frame. When you call a function, it needs to make a new region of the stack to keep track of variables and arguments. RBP just points to where that starts for that function call. And at that value, it points to where the last base pointer was from the previous function. So kind of a little diagram. When you call a function, the arguments are pushed onto the stack, then the return address, where that function is going to go back to when it's done. We then push the saved base pointer and point RBP to it again. And then we push our local variables. And RSP always points to the top of the stack. So the most recent local variable or whatever that function ends up doing. And that will all grow towards lower memory regions. So for a simple function like this, we push on our argument A, the return address of the base pointer, that's where RBP points to. And then we have 3 local variables, all which get added to the stack. And RSP always points to the most recent one. So that's kind of how our registers manage our stack. And so we can get this automatic deallocation of memory. Yes? It's non-deterministic. Sometimes, depending on how the compiler wants to set up its values, what ends up where may change. So it's dependent on the implementation of declaring variables. It could be the other way. It could be completely random. With that, do we have any further questions? Yes. It would push the arguments in order. So RBP points to a position on the stack. At that value is where the last base pointer should be. right? So main will call a function. Main has a base pointer. So when it calls that function, at the saved base pointer is where main's base pointer was. It's confusing, but like, don't worry about it. It's just so computers can manage its functions properly. It's the big thing is the base pointer acts as like index 0, right? I can access all my local variables and all my arguments by some offset from the base pointer. Yeah. All right. So I put this here because one, we chunked through a bunch of definitions, and two, if you end up doing research on your own to get better at assembly, you're going to encounter two major syntaxes. Because with anything that has existed for 44 years, x86, is bound to get more standards towards it. So when Intel made the 8086 microprocessor in 1978, AT&T started using it, and of course, they developed their own syntax for it as well. So this presentation and all the challenges, the only resources I give you are in Intel syntax. But I do want to point out differences so that if you find something, you know what you're looking at. So AT&T prefixes all of its registers with % signs. AT&T also prefixes all of its constants or immediates, which show up in its codes, with $signs. Okay. When we're doing a command in Intel, we do the mnemonic, we do the destination that we want our result to be stored in, which is also used as the first argument a lot of the times, and then we do any other argument that we want for our mnemonic. All right, so it's destination and then sources. And in this case, I'm adding a 32-bit register and a 16-bit register. For AT&T, you add 3 suffix letters and swap the destination and sources, which can get gross. So that's why we're not doing AT&T. Also, comments, Intel uses semicolons, AT&T uses the familiar double slash. Just things to keep aware of when you're looking at assembly code. So with that in mind, the basic to assembly for Intel is the mnemonic, what are you doing? The destination, where do you want it stored? And also the first argument, and any other sources. So this add just adds the value in RBX to the value in RAX, and it's stored in RAX. Sub is subtract. In this case, I'm using an immediate value. So that's immediately available to the processor. It doesn't need to pull it from a different register. Another one I wanted to point out is this XOR RSI. Can anyone tell me what the end result of that command will be? Yeah, you will see this everywhere. This is usually a compiler optimization to keep the program size down. Because when you use a move command, which just moves one value to another, you can use an immediate. However, in certain cases, you're going to have to move a 64-bit value into that register, which means that command will be about 10 bytes, whereas most XOR commands are 2 to 3 bytes. So if you see this a lot, this is just a cheap way to zero out a register. IMUL, IMUL is integer multiplication. This is also a case where there's 2 more sources instead of just 1, but there's like 2 overloads for IMUL with just 2 registers or just even 1 register. So that's kind of what assembly is pointing out here. Usually straightforward. Most of the time you have to read the manual to understand what a command does, because not all mnemonics make sense. With that, I want to talk about logic flow, because most of code that we write has if statements and for loops and while loops and what have you. Assembly provides jump, and you jump to a memory address to to start moving your code to somewhere else. In most cases, those jumps are close or short. So when the assembly gets written, it's actually a relative jump. It says, hey, jump to 28 bytes before in instruction memory, which is good because it's a bit safer, and also you don't need to keep track of where your program has started. Ideally, this is only one of the few ways to modify RAP without completely bricking your program. The other thing that's available is assembly compares 2 values by just subtracting them. because it tells you a lot. If you get a 0, then the values were equal. If you get a positive number, then you know that A was greater than B. So compare just subtracts 2 registers and sets a bunch of flags in a different special purpose register called R flags. If you look at GDB and you print out the registers, it will print out what the R flags register state is, and in words, what all of the flags are true. So parity, carry, positive, negative, 0, so on and so forth. So there's a class of 64 jump commands called GCC, and CC is replaced with like any, not equal to, greater than, less than, so on, which check the flags in the R flags register and then jumps if necessary. So I wanted to kind of step through a bit of code of what that kind of looks like. We have RBX and RAX, we move 32 and 21 into each of them respectively. What I then do is I have these labels. Labels act as like a nice way to define the start of some block of code. And when writing assembly, our assembler will figure out what those labels should be relatively. So it allows us to set it up nicely for us, and then the assembler takes care of it. So I compare those 2 values, and if they're not equal to each other, I jump to bar. Bar will then decrement RBX and then jump back to foo. So this will run until RBX equals 21. When it does, it will zero out RAX and then return in whatever function that I'm in. So that's kind of how logic flow will work. What's up?
What would this actually look like?
This would look like a while loop that decrements a value until it equals 21. So like while I is greater than 21, decrement I. And then zero out B. So that's kind of what you're looking at for logic flow. So then comes the more complicated part, using the stack. There are 2 special purpose like commands to manage your stack very nicely. You've got push, which allows you to just supply a register or an immediate value and push that value onto stack. RSP gets automatically decremented in that case. Or you've got pop, which will take that value, take the top value off the stack, put it in a register, and automatically increment RSP. So that allows you to do that automatic memory allocation without needing to explicitly mess with RSP. If you want to reserve values for local variables, that is done by yourself in the function. So a little example here, I have 4 lines of assembly, our stack, and the states of RAX and RBX. They're initialized to whatever, doesn't matter. I start by moving leak code into RAX, all right? I then push RAX, the value of RAX, onto the stack. This increments RSP to point to that new value. Then I zero out my RAX register. I don't want it to have that value anymore. When I pop, RBX becomes leak code and RSP gets automatically decremented off the stack. This, importantly, does not remove that leak code value from the stack. We've just decremented RSP. If you were able to view that piece of data on the stack without moving RSP, it would still be there. This is very important when we get to security features and security leaks in Pwn next week. So kind of the final big thing I want to talk about is syscalls. Calling functions is a little complicated and involves a lot of like managing memory and saving registers, and it's a mess. However, we care about syscalls because they can do a lot. Because unlike functions that you write in your code, syscalls are provided by the Linux kernel. They are functions that your program needs to use to interact with the computer. If you want to take input from the user, or if you want to open a file, or if you want to check the ports on all of your sockets to connect to the internet. glibc, the standard library, provides wrappers, but you can avoid that entirely with a special syscall command. So one of the most important ones that we'll talk about over the next week is execve, which allows us to run a program on the computer replacing our own. For example, a shell, so we can get full access to the computer. What's up? Just like, so it's a normal written function in C, and inside that, it calls the syscall. So glibc will like provide more error checking for you and make sure that you are calling the syscall properly. But at the end of the day, it's going to call the syscall by itself, just somewhere else in your program, because glibc is linked elsewhere. It's not directly built in your program. Does that make sense? Oh. So calling a syscall. There's a massive table of syscall IDs that is available on the Linux GitHub. This is the most up-to-date resource at any given time, depending on how often Linux changes. But there's other tables to access, which I've linked at the end of the slide, and it's on the meeting flag as well. So what you would do is, if you want to call, I think read is number 0. If you want to call read, you would load 0 into RAX, and then you need to load your arguments into the registers. So in order, for however many arguments that syscall might have, you would load it into RDI, RSI, RDX, and then R10, 8, and 9. That allows you to call all of your syscall with the arguments that it needs. And then if that syscall returns a value, it's going to replace RAX with the new return value. So a couple examples for like basic syscalls. If we want to call exit 10, OX3C is the ID for exit, and then OXOA is 10 in hex. So we move that to RDI and then call syscall. This would just exit our program with a return code of 10. The other one that is going to be important is execve. So the ID for execve is OX59. I make an assumption here that somehow, in some way, we got the characters /bin/sh on our stack. So what I end up doing is I'm moving the RSP value to RDI. This gives me a pointer to the string bin/sh. All right, so that's how I loaded my first argument. I then zero out RSI and RDX to get the null values, and then I call syscall. What this will do is replace my program with a shell. So I have full access to the computer now, if that was not intended already. And finally, the last thing I'll talk about is pointers and dereferencing. I don't know anyone's familiarity with pointers. However, if you're aware that like a register can have a memory address that points to some other data, right? In assembly, everything is just a number. You have to tell assembly whether or not to treat it like a number or treat it like a pointer. So at a high level, if you want to dereference that pointer, you would just wrap it in braces. So that command at the top there would just move whatever's pointed to by RBX into RAX. The other important thing that we do in C a lot, and just in coding in general, is iterating through arrays. So what x86 allows you to do is, on top of having some base address of where your array is stored, you could have an index register, which tells you what element of the array to get. And then you might need a scalar, because if you have integers, those are 4 bytes, longs or doubles are 8 bytes. So you're going to need to multiply that index by some scalar. And then it also, for whatever reason, also provides a displacement on top of that. What's up? So RBX is the memory location. All right. So if my array is stored at OX1000, then RBX stores OX1000. If I want to get the 6th element of that array, I would store 6 into RCX. And if I'm using integers, I would need to multiply that index by 4, because in an integer, there are 4 bytes to an integer. Longs are 8 bytes and so on. So I would need to take my index register, multiply it by that scale of 4, which is provided as like a compiled byte without it being like directly necessary. And that allows me to get the 6th element in an array of integers. Yeah. Yes, you need the starting address, and then from there you could run a loop to increment RCX.
So is it kind of like an offset thing?
Yeah. RCX is like, if you've done like an array and then in braces like 7, RCX is that 7. Yeah. Anything else? Did I hit this? Okay. And then finally, like you can write to memory in the same way. So increment is a writing operation. So if I dereference RSP, this increments the top value of the stack by 1. So I provided, this is all available on the meeting flag challenge, so in case the slides aren't up immediately. These are a bunch of resources I really like and have proven very useful to me. Read the manual. Unfortunately, I cannot cover everything over 44 years of standards. This website is really good because it will explain what every command will do, what you need to pass to it, and then in pseudocode, what that command does, which is oddly circular, besides the point. The other thing I highly suggest you use for the challenges that are available is this online assembler. This just allows you to write assembly, and then you click on like x64 and then assemble, and then you get the bytecode. You're going to need that bytecode to pass into like Python or into your program so you can run shellcode for the challenges that are available. Chromium OS, because it's based on Linux, has a Syscall table and the argument convention available. That allows you to just know what you want to do if you want to call like exit or read, write, open, exec, so on. Two others, if you want to go a bit further, is the flat assembler or FASM, really designed for on your computer compiling assembly for a program. It's a little more tedious to use because you need to be a bit more proper. I've skipped over like the things necessary to write a full program in assembly. But it's nice to have if you want to explore with it. And the last thing, which has been added to this by recommendation of GCE, the compiler explorer. This thing's great. You give it C or a bunch of different languages, and then it just shows you the assembly and highlights what parts of code corresponds to what assembly. It's also useful to see the insane optimizations that some compilers make, like finding closed forms of for loops and so on. So very useful if you kind of just want to explore how compilers are doing this under the hood. I have 5 challenges available. In order, they're adder, lever, reader, shellcode, and modifier. They all accomplish different things. Oddly enough, for what I want to accomplish, the earlier challenges have more complicated source code than the later ones. If you need help understanding what the code does, feel free to ask. However, I highly recommend you use Pwn tools. If you don't have it installed, you can install it with like pip3 install Pwn tools. Everyone's Pwn tool script for all 5 of these challenges should be 4 lines. Importing, running the program, sending your shellcode, which will be a string of bytes, and then going into interactive to see the flag or use the shell that you might pop. That's all that's necessary from Python. The rest of it is up to you writing in assembly. And then next meetings, this Thursday, we have Pwn 1 with Kevin, which will talk about the basics of binary exploitation, overflowing the stack, overriding the return address that we mentioned before. And next Sunday, tentatively, should also be Kevin, talking about more advanced things involving printf and format strings and all that good stuff. Cool? All right. If you have any questions, feel free to ask me. Other than that, there are 5 challenges available. Go nuts.